We are now going to look at gases, one of the three standard physical states. Gases are characterized by being a low density fluid. So gases are about 1,000 times less dense than liquids. They are both fluids in terms of the flow. They will take a container shape, except that a gas is also is compressible and expandable. So gas does not have fixed volume like a liquid does. So gas will fill a container completely, whereas a liquid will fill the bottom portion of the container. Gases are defined by or characterized by four properties. Gas pressure. We measure atmospheric pressure as a way of identifying whether it's going to be sunny or rainy. Gas temperature. We may check the temperature outside before we go out to decide what to wear. But that temperature is the temperature of the air. So it's the temperature of the gas, air. We have volume. When we have some type of container, the container has a volume to it, and it might be a fixed volume or a flexible volume like a balloon. And inside that container we can define how much gas is present, how much. And if we have a low pressure in our tires, we add more gas. If our balloon is small, we add more volume. And the way we measure amount of gas is in terms of moles. And these four properties are sufficient to describe what we call ideal gases. Ideal gases do not depend upon the identity of the gas. So the first property we'll look at is pressure. Pressure is defined as force per unit area. So we're going to be looking at surfaces for pressure. So we'll be doing areas of surfaces. So if we can easily take an area of surface, square inch, square meter, square centimeter. But what is the force being put onto that surface? That force is the collision of gas molecules. They come in one direction, hit the surface, and they bounce off in a different direction. They change directions. The only way they can change directions is by application of force. There's conservation of both momentum and energy going on. So if they change direction, that means that surface they bounced off of is applying force to them. And they are also equally applying the same amount of force to the surface. And this force from the molecules bouncing off, this depends upon how many molecules are bouncing off and how much energy those molecules have. So it depends upon the frequency of collision and the energy of collision. The energy collision depends upon velocity and mass. As we know from the equation for kinetic energy, energy is 1/2 mass times velocity squared. When we want to measure pressure, if we're measuring atmospheric pressure or barometric pressure, we use a barometer, or we call the pressure device a barometer. A pressure device for measuring other gases would be called a manometer, and we can use this to measure both pressure or vacuum pressure. Pressure or vacuum. So most of the time we are measuring gauge pressure. Gauge pressure is the difference from inside to outside. So pressure means that the inside pressure is greater than the outside. Vacuum means that the inside pressure is lower than outside. We can also measure absolute pressure, which is the pressure not dependent upon the outside pressure. We have a variety of units of pressure that we can use. And this line up on top is showing the relationships between all these. All these values are equal to 1 atmosphere pressure, which is the pressure at sea level with good weather, since pressure barometric changes with weather. So 1 atmosphere, that is 1 atmosphere. So the pressure at Malibu on a sunny day is 1 atmosphere. Because our standard traditional way of measuring barometric pressure was using mercury, a column of mercury. We use the height of that column of mercury as a unit of pressure. We measure that in terms of millimeter of pressure. So in terms of millimeter of pressure, a column of mercury would be held up 760 millimeters of mercury high by atmospheric pressure. That millimeter of mercury is also defined as the torr, T-O-R-R. So that means 1 atmosphere pressure is 760 torr. The SI unit for pressure is Pascal. So when we need to be converting between properties outside of the ideal gas law, we probably will be using the Pascal as our unit of pressure. In the ideal gas law, we have defined the ideal gas constant to allow us to use the atmosphere. The Pascal is equal to atmosphere at 101,325 pascals. So 1 atmosphere is 101,325 pascals. So that's a large number. So in common terms, like on the size of our tires, we will list pressure needed in terms of kilopascals. 1 atmosphere is 101.3 kilopascals. And another metric unit, which is becoming more popular in use, is the bar, short for barometric pressure, bar, and that is very close to the atmosphere but not equal to it. It's 1.01 bar. But that's not the full value. It's really 1.01325 bar. The same number of conversion for Pascal, but 100,000 different. So a bar is 100,000 pascals, 10 to the 5th pascals. So we should know that 1 millimeter mercury is 1 torr, that a bar is 100,000 pascals, and we should know their conversions all the way across this second line. We tend to use mercury, traditionally use mercury, because it's a very dense liquid. So that way we can measure atmospheric pressure in less than a meter of height. Because mercury is a persistent, environmentally persistent toxin, we're moving away from that. And then other times we have a more convenient fluid to use. The most common one there would be water. We measure pressure of water in terms of its height. If we want to relate the pressure of 2 different liquids, the density of the liquid times the height of the liquid is proportional to pressure, which means that we're allowed to use the density times height of one liquid, and that will be equal to density times height of a different liquid at the same pressure. The laws of gases have been created in series based on 2 properties at a time. It is easy for us to analyze 2 properties at a time. Harder for us to do 3, 4, 5 properties simultaneously. So we do 2 properties at a time by holding the other properties constant and then seeing what happens with the 2 properties we're examining. And we can do this at different sets of constant other properties to see if that affects our relationship that we get. The relationship between pressure and volume in a gas when we hold temperature and amount of gas constant is called Boyle's law. If we examine the volume of gas as we change pressure, as we increase pressure, volume decreases. As we decrease pressure, volume increases. These 2 properties are inversely proportional to each other. They move in opposite directions. One of the ways that they can be inversely proportional to each other is given by this equation down here. Volume equals constant K over P pressure. So we use V for volume and P for pressure. So we're saying that volume is proportional or equal to 1 over pressure. It will be proportional to 1 over pressure or equal to 1 over pressure times a constant K, our proportionality constant. This is what we find. There are a couple other ways that properties can be inversely proportional to each other. So that means that when we plot volume versus the inverse of pressure, 1 over P, we end up getting a straight line. And that slope of the straight line will be equal to our constant. And intercept will be 0. Intercept would be 0. That would mean that at 0 volume, the inverse of pressure is 0, which at the limit would be 1 over infinity is equal to 0. So as pressure goes to infinity, volume goes to 0. As volume goes to infinity, pressure goes to 0. Well, if we take this equation here, multiply the pressure across, we'll end up with this version of Boyle's law. Pressure times volume is equal to a constant. Well, again, that's at a constant temperature and constant amount of gas. So this constant changes as we change temperature and we change amount of gas. But if we have a set amount of gas at a constant temperature and we see a change in pressure and volume, we can use this version on the bottom. Pressure times volume is equal to a constant, which means it's equal to pressure times volume. So our initial pressure times volume is equal to our final pressure times volume. And this is the version of Boyle's law that we will use for our calculations.